this mirror. This is called a convex mirror, mirror that bends out towards you. Convex mirror, if you look at your image in here, number one, are you upright or inverted?
Upright.
Okay, you're upright. Should your magnification be bigger than 1, equal to 1, or less than 1? Less than 1. So your image is smaller than what you actually are. Your image is right side up. Where does it appear to be? That's a little trickier. Further away from you? Yeah. So the image appears to be back behind the mirror. This is going to be a virtual image as well, just like the flat mirror. It's going to produce a virtual image.
How is that one less than 1?
If you took a ruler and actually measured your image, and then took a ruler and measured how tall you are, would they be the same?
Image smaller. Oh.
Yeah, image smaller means your magnification is less than 1. Convex mirrors are used in convenience stores, for example, hospital corridors, blind driveways.
So do you have an example of a mirror that would make everything upside down?
Yep, we'll get there. So a convex mirror. Let's keep our object out here. Now, so our mirror's bent out towards the object. The focal point. The focal point can be found as if you draw a light coming from far, far away, it will reflect off the mirror at the same angle it came in at. If we draw a couple of these lines coming from far away and reflecting off, and project them backwards, project the reflected light ray backwards, where they appear to cross is the focal length. That's the focal point. The focal length is how far that is from the surface of the mirror. So the focal length is this distance. So I'm just going to the outermost portion of the mirror into this focal point. And that is the focal length. All of those values, the S and the S prime and the F, those are all measured from the surface of the mirror. Okay. F is still R over 2. That's still perfectly valid. Our equation for magnification still negative S prime over S. The absolute value of the magnification is still H prime over H. Those equations are still perfectly valid in this case. Our focal length is not going to be infinitely large, though. If you imagine this as part of a sphere, it's going to have a finite size. It's not going to be infinitely large. So there will be a value of F that's not infinity. Now, one side note, with the focal point being back here behind the mirror, that makes it a virtual focal point. Just like virtual images, negative S prime, these have to be negative focal lengths. So when you plug in your focal length, you need to make sure you plug in a negative value when you're solving equations with a convex mirror. Now, to represent graphically where an image will show up, we can draw a couple light rays from an object and predict where it will be. So I'm going to draw a reference line, first of all. You can think of that kind of as being a floor or something like that, if you want. It's just going to be a reference line. That's the line that goes straight through the middle. Light that came along this line would reflect straight back. The focal length lies on this line, so we have a negative focal length. Now for our object. Our book is incredibly creative, or not. We use an arrow. So something just basic, simple. We use an arrow to represent the object. It doesn't have to be an arrow. You could draw a person or something if you want. We're only going to draw a couple of light rays. We're going to draw 2. You can certainly draw more, but if you want to draw more than 2, then you need to be a lot more careful in your sketching. Okay? With 2, I can freehand it, and we can get a good idea of where the image will be. I'm going to draw both light rays as if they're coming from the top of the arrow. That way, wherever they cross, or appear to cross, will be where the top of the arrow appears to be for us in the image. So one light ray. If I go from the top of the arrow straight to the mirror, it's going to reflect backwards along the line that would go through the focal point. So that's one of my light rays. My other light ray I'm going to draw a line, well, heading towards the focal point. So I'm heading towards the focal point, but when it hits the mirror, it's going to reflect off parallel to our reference line. If we project backwards the reflected light rays, now the reflected light rays themselves are going to diverge. They're never going to cross each other. So we can only get a virtual image in this case. Whenever the light rays diverge, we project them backwards behind the mirror. Where they appear to cross right here is where the arrow, the tip of the arrow appears to be. Since we drew the light rays from the tip of the arrow, where they appear to cross has to be the tip of the arrow. The base of the arrow has to come down and touch this reference line that we've drawn. So that's our image. This is our image. This is our object. Object distance, S, is right here. Image distance, S prime, is right here. Notice the image is smaller than the object that we drew. What mathematically would we have to come up with to represent a smaller image? What mathematical quantity would tell us about how big the image is?
A lot less than 1.
The numerical value of m. Exactly right. So if we were solving for the numerical value of m, it would need to be less than 1. Our image is upright. The arrow was pointing up as the object. The arrow was pointing up as the image. Mathematically, what will represent that our image is upright? Positive m. Exactly right. So we're going to get, if we were plugging in numbers, we would get a magnification value that was positive point something. Something less than 1. This image is virtual. So mathematically we would need to come out with a negative value for S prime. Okay? So for example, It is a big one. So we're looking into a shiny Christmas ornament, one of those balls. The ball has a diameter of 8 centimeters. Where does your image appear to be if you're holding the ball 20 centimeters from your face? So you hold the ball in your hand, you're smiling at yourself in the ball. Where will your image appear to be? And let's also find the magnification. So, what importance does the 8 centimeters have to us?
That tells us the radius.
We'll be able to get the radius. So the radius, if the diameter is 8, then the radius is 4. If the radius is 4, then the focal length is 2. We have to be careful though. With a convex mirror, the focal length is virtual. That means it has to have a negative value. So we do have to put the negative sign on the focal length. So we know the focal length. What's the 20 centimeters?
S.
That's S. Fabulous. So having F and S, we can easily solve for S prime. 1 over S prime will be 1 over F minus 1 over S. 1 over negative 2 centimeters minus 1 over 20 centimeters. We can get a common denominator, 20 centimeters, 10. So negative 10 over 20 minus 1 over 20 will be negative 11 over 20. But please keep in mind, this is 1 over S prime. Right, so S prime will be 20 centimeters, sorry, negative over 11, negative 1.82, 1.8 centimeters. What this answer tells us, notice we came up with a negative answer. That's good. The negative answer means it's virtual. That's what we get with convex mirrors, is a virtual image. So that's what the negative sign means. 1.8 centimeters. This means your image shows up as if it were 1.8 centimeters from the surface of that ball. Behind, so you look like you're inside the ball, and you're 1.8 centimeters behind the surface.
So with convex mirrors, will F always be negative?
Yes. Yeah, convex mirrors, you will always have a negative focal length. So as you're doing problems, like this one for example, it doesn't tell you that it's negative, but you need to know, since it's convex, that it will be negative. So you have to put the negative sign on yourself. Questions on getting this answer, or what it means? Magnification. Negative S prime over S. Negative. S prime is negative 1.8 centimeters. S is 20 centimeters. Negative times a negative is a positive. 1.8 divided by 20.09. Okay, this answer has two meanings. Positive sign. The positive sign in and of itself means your image is upright. If you're sitting upwards, your head on top, your image, you're sitting upwards with your head on top. Okay? The 0.09, since it's less than 1, means your image is smaller than the object. This means your image is 9% the size of your object. If your object was 1 meter tall, then your image is 0.09 meters tall. Yes?
Question. On the convex mirror, when we looked at it, everything appeared to be farther away.
That's where the virtual image is.
Yeah, and so that's saying it's 1.8 centimeters farther than 20 centimeters on the other side of the mirror?
It's 1.8 centimeters from the surface, behind the surface of the ball. It's 1.8 centimeters back this way.
Alright. is where the focal point is.
No, this is the image. S prime is the image. So 1.8 centimeters is your image distance. So the image appears behind by 1.8 centimeter. That's what that means.
Because I was just thinking if you're 20 centimeters away from it, and when you're looking in the convex mirror, it should appear farther away. It just
Yeah. So this was 20 centimeters. This is 1.8 centimeters.
No, you look closer but smaller is what it is. You don't look farther.
Well,
To your
we need to
perception.
define how we're saying that. We look closer to the mirror than we actually are, yes. But we look like we're behind the mirror. Okay?
so it's just thinking like with a flat mirror, we still look like behind the mirror, but
You should look behind the mirror here too. Your image should look like you're behind the mirror.
saying like with a flat mirror, shouldn't we appear closer to us than with a convex mirror now?
No, this brings it closer. This brings it closer to the surface.
Well,
Right.
The perceived distance of the object in the mirror.
Right. Exactly right. So it brings it closer to the mirror being convex. That's why you actually get a wider field of view with a convex mirror. That's why they use them in convenience stores, for example. So the attendant can look up at the mirror and see what's going on in multiple aisles. Because you get a bigger field of view. That's why they use them in hospital corridors, so you can see if someone's running down that hallway when you're coming down this hallway, so you don't run into each other.
Smaller mirrors on cars are always convex.
Mm-hmm. Yeah, the small circular mirrors on your side mirror are convex as well. That's why they say objects in the mirror appear closer than they or are closer than they appear.
For magnification, is there units associated with that?
No. Yeah, because the centimeters, for example, here cancel out, so it's just a number.